Okay. Okay, in this video we will discuss infinite series, that is equivalently infinite sums. To understand what these things mean, okay, let us consider first as a motivation the examples. The first example is 1 plus 1, 1 minus 1, plus 1 minus 1, plus 1 minus 1, and it continues like that up to infinity. Okay. The second example is a similar one. Again, it continues up to infinity. These are infinite sums. Okay. We see that everything cancels everything else, and so at the end we get 0 in both cases. Now, here of course you may not be aware of it, but we made use of our knowledge of finite sums. That is, everything cancels with everything else. What that means mathematically is not clear at all. What is not clear at all is, what is an infinite sum? We did not define anything like this as an infinite sum. Okay? So let us try to answer that question first. What is an infinite sum? That means we are adding up to infinity. What that means? By now, we should have understood that when you have the expression up to infinity in a mathematical statement, it means a certain limit all the time. So, how could we define these things, or in general, something like this? We add it up to infinity. What is the meaning of this? Okay. To obtain a meaning for it, okay, let us try to consider this as a limit. Okay. Well, what we should do is quite obvious. Okay. Let us define this infinite sum step by step. So, let S1 be A1, S2 be A1 plus A2, Sn be A1 plus A2 plus An. All are finite sums. And then, okay, define as the limit of Sn, which means that n goes to infinity, it would be it goes up to infinity, so we get an infinite sum. So, such an infinite sum is the limit of the sequence Sn where we are adding up to it. Of course, when we have such an infinite sum on the one side, and it means the limit of Sn, it's not clear that this limit exists. Maybe it does not. So this is the precise question. Now, let us go back to the first example. In 1, okay, S1 would be 1, S2 would be, remember, A1 plus A2. So it is 1 minus 1, it is 0. S3, okay, would be 1 again. S4 would be 0, and it would continue like that. Okay. Clearly, this says that S2n would be 0, S2n plus 1 would be 1. Now, okay, because these are constant sequences, their limits when n goes to infinity are themselves the constant value, and they are not equal. This means that limit of Sn does not exist. Okay. Well, equivalently, this does not exist. So let us go back, okay, to what we had above. Okay. Call this star. It's not 0 because it does not exist. Now, for example 2. Okay. Let us look at S1. That's A1. That's 1. S2, that's 1 minus 1. That is 0. S3, okay, that's the third term in the sum. Okay, that would be 1/2. Okay, S4 would be 0. You can continue. S2n would be 0. S2n plus 1. Okay, so this means you add all terms with indices 1, 2, 3 up to 2n plus 1. But the first 2n of them add to 0, and you have the next term. Okay? It is, as you can see, 1 over n. Okay? Maybe not. I should put minus 1 here. So it's n plus 1 actually, or n minus 1. So let me put a minus sign. Okay. Now it's correct. Okay, if, for example, you add everything up to 3, it means n is 2. So you have 1 over 2 up to 5, n is 3, and so on. So you can check this directly by looking at the definition. But then, limit S2n is the limit of zeros, so it is 0. Limit S2n minus 1, which is the limit of 1 over n, it is 0. So from our considerations in sequences, this means that limit Sn is 0. So 1 minus 1, 1/2 minus 1/2 is 0. That's correct. So this example, these two examples, okay, serve two purposes. Firstly, they tell us that we cannot regard an infinite sum as if it were a finite sum. Okay. Secondly, we try to understand what an infinite sum means. An infinite sum is a limit of Sn. Well, what is Sn? Sn is the sum of the first n terms. We have special names for these, so let us do some definitions. An infinite series, I will not write infinite all the time. When I say a series, it will be understood that it's an infinite series. A series, A1 plus A2 plus up to infinity, okay, which can be shown as a n from 1 to infinity, okay, is a formal sum, which means that it may not be a number. Okay, because this is the limit of A1 plus up to AN. Okay, when of course n goes to infinity. Okay, a minute ago we called this Sn. So a series is the limit of Sn. Now, if this limit exists, it's a number. If this limit does not exist, it's nothing. But formally, we show it this way. Okay, it's just a symbol. It doesn't mean that something exists. Just symbolically, we show it by this. Okay, the sequence Sn is called the sequence of partial sums for the sequence A, for the series A. And An is called the general term. Note that when we are adding infinitely many terms, we have two sequences in question. One of them is the sequence An. Of course, it's important. It defines the series. But there is a second sequence, which is even more important, because a series has a value that is this formal sum is equal to a number, means exactly that limit of Sn exists. So everything depends on Sn, not An directly. An has a role to play, but basically it is Sn. Okay. Well, at this point, we should note one thing. Okay, let me define the terminology further. Let me finish that part first. So if limit Sn exists, then we say the formal series converges, as in the case of sequences, and write L is this infinite sum. Recall, it's the limit of Sn. Okay. If limit of Sn does not exist, then we say the series is divergent or diverges. So everything, again, depends on the limit of Sn. So Sn sequence is the basic thing in a series. Okay. So, a remark which will emphasize this role of Sn. Okay. Now, if a series is convergent, that is, limit Sn exists. Okay, here exists means, of course, that it is a real number. Okay, we don't say a limit exists if the limit is equal to infinity. Okay, it is a divergent case. So, if a series is convergent, that is, if limit of Sn is L, it means the following. Then we can write this series as a sum up to n plus the remaining terms added together. Now, what happens here? This is nothing but Sn. This is nothing but the limit of Sn. So, okay, what happens to the far right term? It must go to 0. Actually, in this case, this is L, this is a finite sum, this is an infinite sum, but it's very small. Okay, it must go to infinity if n becomes larger and larger. This is sometimes called the error term. We will return back to it later. Okay, so, okay, limit of Sn is L, happens exactly if limit of this term is 0. This is the small part that we have in a series. Of course, this means if and only if the series converges. So convergence of a series means this remaining part goes to 0. It looks like a large term, but it is not. Okay, in a convergent series. Okay. Well, the next argument is how can we find the limit of the value, rather, of an infinite sum, or the limit of Sn. How can we find it? So, let us consider some examples. Okay. How can we find the exact value of an infinite sum? Well, we know that, okay, this value, that is, this sum, is limit of Sn. So, to find what this is, we have to find the limit of Sn. Now, to find the limit of Sn, we have to find Sn itself. Okay. So, we need to find Sn in explicit form so that we can take the limit of it. Now, how can we calculate Sn, that is the sum of first n terms? It is not that easy if you don't have just nice numbers and special cases. Okay? You need to specialize on a few basic examples. Let me give you two of them. The first one is the so-called geometric series. This is of the form a sum n from 0 to infinity of r to the n. Well, n can start from 0 or 1. It doesn't matter, actually. We will just check that a minute later. Here, r is a real number. And, okay, the 0th power of anything will be taken as 1. Okay. So, in our formulation, this means 1 plus r squared plus and so on. It's an infinite sum, okay? But it continues by multiplying the term with another r all the time. Okay. Now to find Sn, you have 1 plus r squared plus, you stop at r to the n. Well, here there is an indexing problem. Okay, you can modify it in any way you like. If you have a difficulty with the indices here, always look at the open form. The open form will guide you to a correct calculation. Okay, the argument is multiplying this with r. You have r plus r squared plus r to the n, and finally r to the n plus 1. Now, if you look at the difference, that is Sn minus r Sn, okay, everything cancels here. Okay. So you have 1 minus r to the n plus 1. Okay, thus Sn can be found as 1 minus r to the n plus 1 divided by 1 minus r. Of course, we have to be careful here. This is true if r is not 1. Okay. If r is 1, what happens? Okay, look at the series. If you put r equal to 1, all powers will be 1. You will be adding 1s. If you add 1s, okay, your Sn will be n plus 1. So, diverge. Because it diverges, that analysis is completed. So we work with what happens if r is not 1. Well, then we know Sn. We can take its limit. So, limit of Sn will be 1 over 1 minus r, 1 minus limit of r to the n plus 1. Well, when does this limit exist? Okay. If r is bigger than 1, of course, its powers will be larger and larger, and it will go to infinity. So there will be no limit. If r is less than minus 1, it means in absolute value it's bigger than 1. So its nth powers in absolute value will go to infinity. So there's no way that it can have a limit. So this exists only if R belongs to the interval minus 1, 1, 1 included. But we assumed R is not 1. So it exists if and only if absolute R is less than 1. That is, R is between minus 1 and plus 1. Okay. So this is an example where we can determine what Sn is exactly, so that after that we can take the limit and have our analysis done. Okay. Let me formulate this in other words. So we conclude that a geometric series, okay, here one can take n equal to 1 or whatever, it doesn't matter. This converges if and only if absolute R is less than. Because this only means that you don't take the first term, but it doesn't affect the limit. The limit is something about what happens when n goes to infinity. So geometric series convergence is characterized by absolute R being less than 1. Now, maybe a little exercise for you. Show that this has nothing to do with limits or anything. Show that actually it does. Okay. And starting from n to infinity of R to the n happens to be R to the n times 1 over 1 minus R. Okay. Assuming, of course, you have convergence. Okay. You can easily show that. Everything depends on the calculation of Sn's, remember. So you have to be careful about Sn's. A second example is a series where an is of the form bn plus 1 minus bn. Now, this is such series are called telescoping. Okay. The reason will be clear in a minute. This is a different type of sequence where we can calculate the partial sum sequence Sn. Let us try. Okay, Sn happens to be A1 plus A2 plus up to An. Now that is, now let us write down what A1 is. It's B2 minus B1 plus, okay, it's B3 minus B2, and it continues up to the last term, up to n. It is Bn plus 1 minus Bn. Note that because of their form, all these terms cancel out. And you're left with, okay, Bn plus 1 minus B1. Which means that, okay, we have now what Sn is. So, limit of Sn exists if and only if limit of Bn exists. Okay. And limit of Sn is limit of Bn minus B1 in this case. Well, you will see that in practice, sometimes we have not Bn plus 1 minus Bn, but the opposite, Bn minus Bn plus 1. It just means that you multiply the whole series with minus 1. So the arguments don't change at all. Okay. Well, some examples of telescoping series. Now in this series, let us see if we can observe that An, which is 1 over n plus 1, can be written as a difference of two consecutive terms of a sequence. Of course, you will recall that in integration techniques, we had a partial fraction method, so we can divide this into partial fractions. That's a trivial matter. This is nothing but 1 over n minus 1 over n plus 1. So, if we call this Bn, this becomes Bn plus 1. So it is of the form Bn minus Bn plus 1, which means if you multiply it with a minus sign, you get the standard formulation. And of course, limit of Bn here, which is limit of 1 over n, is 0. So, okay, if I consider the negative of 1 over n plus 1, 1 to infinity, it would be the limit of, okay, minus the Sn's, okay, which happens to be the limit of, okay, here it becomes B1 minus Bn. So it is B1. And B1 is 1. Actually, I had a minus sign somewhere. This would be limit of minus Sn, that's right. And minus Sn, you change the places. So it would be limit of, sorry, you have here Bn and then B1. Okay, so that would be minus B1. Okay. It means that the limit in question This one. So what's the advantage in telescoping series? In telescoping series, we can calculate what Sn is exactly and take the limit. Sn is nothing but Bn minus, or Bn plus 1 minus B1. I can put plus 1 here. In the limit, it won't change. So this part is the same as limit of Bn plus 1. So I don't write n plus 1 or n because the limits are the same. Okay. Well, let us consider a different example of telescoping series. Consider the sum of logarithm n plus 1 over n. Okay, you're adding the logarithms, etc. But if you look at it from the telescoping point of view, this is nothing but the sum of logarithm n plus 1 minus logarithm n. Of course, you call this Bn. This becomes Bn plus 1. So, Sn, okay, I will not calculate it again, is nothing but logarithm of n plus 1 minus logarithm of 1, which happens to be 0. When we take the limit, of course, it goes to infinity. Which means that limit of Sn does not exist. Okay, so the series is divergent. So because we know what Sn is, it's easy to decide whether the series is convergent or not. Sometimes this is not very obvious. Okay, I will not complete the third example, but let me just tell you the hint, and then you can do it yourselves. Okay, here x is a fixed real number. Now, this is a very difficult series to check for convergence or divergence, okay? But let us observe the following hint. Now, in trigonometric products, the product of sine A and sine B can be represented as a difference of cosine functions. So, okay, consider sine x over 2 times sine nx. This happens to be 1/2 of cosine A minus, that is nx, minus x over 2, A minus B, minus cosine of A plus B. Okay. Let me check if I wrote it correctly. Yes. What does this say? This says the following. So, sine nx can be written as 1 over 2 sine x over 2 times cosine 2n minus 1, okay, over 2x minus, okay, 1 over 2 sine x over 2 cosine 2n plus 1. over 2x. So if you call this your Bn, this becomes Bn plus 1. Of course, we have to be careful. In this argument, well, this is always true, but when you divide by sine x over 2, okay, it may be 0. It depends on the value of x. So x over 2 will not be a multiple of pi. Okay, here, of course, x over 2 is not n pi, or let me say some k pi for any k. Sorry, 2k pi. Okay, x over 2 is not k pi. That's correct. Because if this is true, then actually there is nothing to prove. That means x is 2k pi. If x is 2k pi, this sign becomes 0, and yeah, the convergent series, no question. Otherwise, okay, you can work with this hint. It's a telescoping sum, actually. Okay, but it's not obvious. I will not complete the proof here. Well, you will see more examples on telescoping series in recitations and other things. Well, one last observation about telescoping sums as a fourth example, if you want. As a fourth observation, okay, the geometric series is a telescoping series. Okay, why? Well, assume as before r is not 1, okay. Then, if you consider 0 to infinity, r to the n, okay, you can write it as 1 over 1 minus r, 1 minus r, r to the n. Okay, but this is, of course, 1 over 1 minus r sum of r to the n minus r to the n plus 1. Okay, this is your Bn plus 1. This is your Bn. As we did in our analysis, okay, you can check the limit of r to the n to check whether a geometric series is convergent. It will be convergent if and only if absolute r is strictly less than 1, and that, of course, was the conclusion that we had before. But it follows from the telescoping part as well. So what is our conclusion? Well, maybe a remark. So practically, the telescoping series are the only ones where we can calculate Sn explicitly. Okay, of course, I have to add with our present knowledge. So the second question that follows is what happens if we don't have a telescoping series? Okay, how do we calculate the limit value? Well, it is not easy at all in many cases. In some cases, it's impossible, even though the series converges. The impossibility comes from that we do not know that number as a combination of our knowledge of elementary real numbers. Namely, you cannot write down every real number as a combination of square roots, pi's, e's, divisions, multiplications, and so on. Okay, there are a lot of other types of irrational numbers. So, it may not be possible to find exactly what the limit value is. So let me write this as a part of this remark. In fact, okay. In fact, even if a series is convergent, it's not easy to find its limit value, or possible elementarily to find its limit value. Okay. Let me say here, so this is it. As an example, consider the series 1 over n squared and 1 to infinity. Okay. We are going to show convergence, okay, quite soon. So this is a convergence series, okay? But what is the limit value is something one cannot observe by looking at the series directly. Okay. Its limit, or its value, happens to be pi squared over 6. So even if we know it is convergent, it's not easy to show what exactly the value is. Okay, you can approximate this value, but exactly you cannot find it in an easy manner. One has to use quite sophisticated mathematical methods to show this. Okay, so the next best thing we can do is show that it is convergent. Forget about what it is, what the value is. Okay. If we know it is convergent, okay, by taking sufficiently many terms and adding them together, we can get approximations to the limit value. So we will be content by finding whether the series is convergent or not, and will not worry about what exactly it is. Let me write this down. So we would be content to know that a series is convergent. Okay. Then, since the infinite sum is limit as n by taking large n values, we can approximate the exact value. So the question now is, without calculating the limit of Sn, possibly without knowing what Sn is, okay, we want to say something about the existence or non-existence of the limit. Now, this is called tests for series. In this respect, we have a very important theorem, which is quite simple, but usually wrongly understood. Okay. Note that we already mentioned that in a series, there are two sequences involved. One of them is the sequence an, the other one is the partial sum sequence Sn. Okay. So, this next theorem we have the following. If a series is convergent, then limit of an must be 0. Okay. This is a very general theorem. It applies to all sequences of real numbers. Okay. Convergence implies that the general term, which we did not work on too much yet, must have a limit 0. Okay. It's easy to prove this, so let me just write that down. Okay. Well, consider Sn minus Sn minus 1. Okay. What is this? This is the sum of all terms up to the index n minus 1. This has an extra term, which is an. So this is actually a capital N. But the series is convergent. It means Sn and Sn minus 1 converge to the same limit value. So this goes to L minus L, where L is the infinite sum of A. This is by convergence, but that is 0. So proof is finished. Okay. Now, why is it wrongly understood? We can use this theorem quite profitably in many cases. Let us start to understand what it really says. Okay. Let us look at the theorem from the contrapositive side. That is, okay, from logic, okay, P implies Q is the same as not Q implies not P. This is the negation. So, the theorem says if limit of an is not 0, then the series is divergent. More precisely, okay, what does it mean that limit of an is not 0? Okay, well, it can be something else. Not necessarily. There are two ways limit of an is not 0. One way is it has a limit, but it's not 0. The other one is it doesn't have a limit at all. If it doesn't have a limit, well, the limit cannot be 0. Okay. So this means limit of an does not exist, or limit of an is L, but L is not 0. If there's a limit, not 0 means it's a different value. If it doesn't have a limit, it means directly there's no 0 limit. Now, writing this, we get the so-called nth term test. It exactly says this. That is, if limit an does not exist, or limit an is L, but it is not 0, then the series is divergent. Well, this is a test which is one way. That is, it only tells us that a series is divergent. Okay. Never it says it's convergent. So before, okay, we write these comments, let us see some examples on this. Okay, my first example will be the series we considered before. Okay, now calculating Sn, explicitly we showed that it does not have a limit, and so the infinite sum was divergent. That means such a limit does not exist. Okay. Now here, we can write this as an infinite sum form. When n is 1, you must have 1. If n is 2, you must have minus 1. So, okay, you have minus 1 raised to a power. If the power is even, you have plus 1. So, it's appropriate to put here n plus 1. If n is 1, you have an even power, you have plus 1. If n is 2, you have the third power, so you get minus 1, and it continues like that. So here, an is minus 1 to the n plus 1, and limit of an does not exist. We showed this by looking at a2n and a2n plus 1. Okay. So, okay, the infinite sum or the series is divergent. Because an does not converge to 0. Okay. As a second example, let us look at 1 over n plus 1. Now in this example, we have an, which is 1 over n plus 1, which certainly goes to 0. So the nth term test says nothing. Because, okay, it says that if the limit is not 0, something happens. So, nth term test cannot be applied. Okay. But, okay, we already showed that this is a convergent series. Using telescoping series. It's a telescoping series. We already considered this example. As a third example, consider logarithm of n plus 1 over n. Then, of course, n is logarithm of 1 plus 1 over n. When n goes to infinity, clearly it goes to logarithm of 1, which is 0. So it goes to 0 when n goes to infinity. Okay. Again, nth term test says nothing. Okay. But we showed it to be divergent. So these two examples show that even though nth term test does not apply, okay, the series can be convergent or divergent. So you cannot say anything if an goes to 0. You have to look at other things. Okay.